right, so time to start, 4:05. So it's my great pleasure today to introduce our applied math seminar speaker, Soledad Villar. Soledad is an assistant professor at Johns Hopkins University. She got her PhD in 2017 from University of Texas at Austin. And she spent also a postdoctoral period in New York City at New York University. She's an expert in mathematics, data science, and machine learning. I should be talking about units-equivariant machine learning today. So thank you very much for your visit and for being here. And take it away.
Thank you. Thank you so much for the invitation and for being here in person. That's great. Okay, so please ask questions, or let's make this seminar a little bit interactive if you want. I'm going to talk about some work in equivariant machine learning, and I have some collaborators. Some of them are physicists and some of them are PhD students. So it's an interdisciplinary effort. I guess that one of the reasons why current machine learning methods are so successful at many tasks is because they are, one of the reasons is that they are very over-parameterized, and trying to understand the role of over-parameterization in learning is a very interesting mathematical question. But also it's not just over-parameterization, there's a lot of structure in these models. They have like a lot of especially designed architectures that are successful at different tasks. So for instance, convolutional neural networks are very successful at image processing, and then recurrent neural networks are very successful at text processing, and they are just capturing some structure that the data has in some way. So the convolutional layers are capturing like information existing in like different patches of the image, and just applying the same filters in different parts of the image gives you some specific reasonable structure. Another space where that is very popular these days is this graph neural network stuff. And I know that a lot of this research that I'm mentioning about graph neural networks is done here at McGill and in Montreal. There's a lot of people working in this stuff in maybe different departments like computer science and machine learning. But yes, just like the fact that if you want to learn functions on graphs, you have to have specific structures that are able to capture symmetries that are present in the graph. So in particular, if I'm going to express my graph as an adjacency matrix, then the representation is not unique. You can just permute some rows and columns and get the same graph structure. So if you're going to learn functions on graphs, then it should be agnostic to whatever representation you have of the graph. And that's like one form of invariance or equivariance. I'm going to define what it is in the next slide. And in the case of graph neural networks, people implement it by implementing message passing. So there's some functions that are messages that each node sends to their neighbors, and it's the same function applied for every node in the graph, but the inputs, of course, are different. And that's one way people implement this like symmetry into their models. If anything is unclear, please ask. So I'm going to define what an invariant or an equivariant function is. It's just like if you have a group G acting on your data space X, then you say that a function is invariant if for every possible X input data point and G group element, you have that f of Gx is equal to f of X, just invariant. So it's invariant with respect to this group action. And if your G also acts in the codomain of your function, then you can say that the function is equivariant if f of Gx, h of Gx is equal to G times h of X for all X and all G. And that's equivariant. So I have like this example, like say I have a machine learning method or a function that predicts the positions and velocities of these particles in this dynamical system. So if I take my system and I rotate every particle and every velocity, then the prediction should rotate in the same way. So that's one form of equivariance with respect to rotations. of your, like say, if I apply a rotation to your positions and momentums, then the prediction rotates in the same way. Another example with a different action is if, for instance, if I have this graph, I can represent this graph with this adjacency matrix, but I can also represent this graph with the adjacency matrix interchanging like these two things, like interchanging the order of the third and the fifth node, and that's the same graph. So if I'm going to write it as a function on this graph, say the length of the shortest path that visits every node, this function as a function of the adjacency matrix is invariant with respect to the action of permutations by conjugation, which is this action, relabeling nodes. And if you're learning some function that embeds every node into a vector space, then the function you want it to be equivariant, because if I change this order, the thing should permute in the same way. Does that make sense? That's the invariance and equivariance notion. Okay, so one example of invariant and equivariant functions on graphs or anything are spectral methods. So for instance, if I have this matrix over here and I take the eigenvectors of this matrix, then these eigenvectors are equivariant with respect to permutations, the action by permutations by conjugation. So here, if I change this row and column, then the eigenvectors change accordingly to that, right? And that's the reason why one can do like spectral clustering, because they capture that ordering notion that one has. So for instance, you can use this structure to define another way of parametrizing the space of equivariant functions on graphs without requiring this message passing business that I was describing before. Like you can do it as a generalized like spectral method. You can parametrize functions that behave in that way, that functions that given a graph, it gives you an embedding of every node in a clear space, so that if you take a row and a column and you permute that, then the output permutes in the same way. And the way you do it is by generalizing a spectral method. You take a Laplacian, a generalized Laplacian, which is a linear combination of identity, degree, and powers of the adjacency matrix. You learn how to combine those as you find like a linear combination of these operators of your graph, and then you can define, you can parameterize the class of functions by like taking this power iteration on this Laplacian and enrolling into a neural network. Basically, it's like you take an iterative method, and each of the layer of your neural network is like one step of your iterative method. And then the parametrization would be how you combine these operators. That's like the set of parameters that define the network. You can have it so that, for instance, at every step of this unrolling, the parameters can change, for instance. Yes.
So this, in this context, rho is some kind of thresholding operator?
Yeah, this is like a thresholding operator. Yeah. So this is the one way of defining a class of functions on graphs that is equivariant. This appeared in a paper by Joan Bruna and Zhendao Chen and Li Li in 2017, and they were inspired in like methods, the spectral methods for community detection, like in the stochastic block model when the graphs are sparse. And you can use it to other things like quadratic assignment or max cut and things like that. So the main focus of my talk today is how can we parameterize a space of functions that are equivariant with respect to different group actions? How can you efficiently parameterize that? And what can you say about mathematically this class of functions? What functions can you approximate? How well do they generalize? And and in particular, I'm going to focus on specific group actions that have to do with physics that are useful for physics problems. And the reason why we focus on this is because like the laws of physics do obey symmetries. So if we're going to do something like a n-particle simulation, like the toy that I showed you earlier, it makes sense to incorporate the physical symmetries into the machine learning models, because you expect that that would like reduce the number of samples that you need for learning, and maybe you can quantify how much they reduce the number of samples. And this is a good like place to work on, because the symmetries are satisfied exactly because of the laws of physics. Whereas in images, it's harder to say what symmetries are satisfied exactly. Like, yeah. So in this case, like I think that we do it in this way because it's like a natural place where you enforce exact symmetries. And the symmetries that we will care about are with respect to rotations, translations, and units. Like if you have a system that, say, if all the features of your model have units, like say an energy, a mass, velocity, if you do a units transformation, like a rescaling, everything that has units of meters now has units of inches. That's like a rescaling in your inputs. Then the outputs should rescale accordingly. And how do you implement that? And the group of scalings is going to be non-compact. So there's going to be some complications that arise from that situation. And there's a classical result by Noether in like the beginning of the 20th century that says that every differentiable symmetry generated by local actions are in correspondence with a conservation law, like conservation of angular momentum, conservation of energy, etc. So these physics symmetries are in correspondence with conservation laws. So how can we implement these symmetries? So in practice, people look at data augmentation to implement the symmetries. So they say you take if you know that this cat is a cat, then you can just like make different modifications of the cat that will also be classified as a cat. But in the case of the physics, you can basically think of the data augmentation as like the application of the group element to your inputs, and that's where would be the augmented data space. Also, you can think of doing, since you know that many of these symmetries are in correspondence with conservation laws, you can have a penalization for the conservation law not being held, like for that, and then you can say, hope that this will imply the symmetry that is in correspondence with. But what I'm going to talk about today is how one can restrict the class of functions so that it satisfies the symmetries that we care about. And there's a lot of work in this space by people doing different things like group convolutional networks, parametrization of the symmetry preserving functions using reducible representations, zero CNNs. There's many things. I'm just gonna describe maybe a few of these ideas, and then I'll tell you for some cases, for some groups, the parametrization is very simple to do using classical invariant theory. Okay, great. So why do I care about the symmetries? And I'll have a slide later in this talk explaining how we can show that implementing the symmetry will give you a smaller generalization error and better sample complexity. So you need fewer samples to learn the same thing, just because of the class of functions is restricted, and it gives you like the right inductive bias in some cases if you know that the symmetry needs to be preserved. But the disadvantage of this is that enforcing the symmetries can be hard because maybe if you want to parameterize a class of function that is very restricted, then you may need to have too many parameters. And so there's a trade-off between being able to express everything that is invariant or equivariant and the computational complexity of that. So for example, in the case of graph neural networks, and actually this is a paper that we wrote a few years ago, and it was motivated by some work by Christopher Morris, who is a postdoc here in some department, I think computer science, I don't know. So what they did in this paper, they showed that like this class of functions, these message passing neural networks, these message passing graph neural networks cannot distinguish graphs that they're quite different. So for instance, this graph A is just two triangles. It's a regular graphs with degree 2 and 6 nodes. This graph B is an hexagon, is a regular graph with degree 2 and 6 nodes. And for every choice of parameters, the message passing neural networks, if you implement them like the vanilla implementation of this, will have that f of A is equal to f of B for all choice of parameters. If you just do this message passing without using null features, just the simplest thing. So this shows that actually maybe that's not the right model for implementing this equivariant functions. It just shows that there's like the class of functions that you can express is very restrictive. And then what we did was like took many like graph neural networks architectures and then just compare them in terms of like the graph isomorphism problem. Like what if there's an arrow from here to here, if there is a pair of isomorphic graphs that, if every pair of isomorphic graphs that non-isomorphic graphs that are distinguishable by this class are also distinguishable by the other class. Does that make sense? Maybe I said it in the opposite direction.
Okay, I don't know much about message passing neural networks, but like, can you give me an intuition why these models cannot distinguish between these two?
Yes, it's because they get local updates from their neighbors, and there's not like, if you don't encode it into the informations that you know for each node, like every node is equivalent to every node. So what this thing is going to learn is that maybe it's going to learn that every neighbor has degree 2. And that also happens here, like every neighbor has degree 2. So since there's nothing that tells you that this thing is different from this thing from the beginning, yeah, you have to break the symmetry somehow. So actually the way people fix this issue is by breaking the symmetry, by having a different node feature for every node. Yeah. And that's something that, yeah, and if you look at graph neural networks, there's a lot of research just suggesting new architectures of like how one can implement these graph neural networks so that it's a little bit more expressive than the previous graph neural networks that was defined. And expressive means that it can approximate the class of invariant functions in a better way. So you work in approximation, like in approximation of neural networks, like what kind of functions can you express, can you approximate? So here, I don't know, like what kind of functions can you approximate? You know that every function that you have that you can express is invariant, but in the space of invariant functions, like how much can you cover? How much can you approximate? And so for message passing, I think is known. I think it's like you can distinguish two graphs if the linear program relaxation for the graph matching gives you something non-zero. So like if you look at the linear program relaxation for graph matching, it minimizes in the space of bistochastic matrices this objective. And if this objective is equal to 0, then the message passing cannot distinguish them. If you add more frills to the message passing, then you may be able to distinguish them, but just like if you don't, then that's what you get. And there's a lot of research on that. And some of this research has to do with like polynomial approximation and and you can write these things in terms of Stone Weierstrass. The idea is that, okay, say that you want to find for any group, you can do this for any group. Say that you want to write the neural networks that are equivariant with respect to some group action. So the feed-forward example is just like you have linear layers and then composed with nonlinear activation functions. So linear, nonlinear, linear, nonlinear, right? So then if you restrict your linear functions to be linear and equivariant, then that's a huge restriction. Like, so that, for instance, there's no linear function that is rotation invariant. So then you will need to have something else. So what they do is they say, okay, now I'm going to look at tensors instead of linear functions from RD to RD. I'm going to look at linear functions from RD to the K to RD to the K. These are my linear functions now. And I'm going to ask that these linear functions are equivariant. And equivariant with respect to an action that takes a tensor product. And if Q acting on the tensor product is the tensor of Q acting in each of the factors, right? And so now I'm going to parameterize my neural network as that. And this looks like a polynomial approximation question. So how do you parameterize this and how much can you approximate? So for some groups, it's known that if you make the order of the tensor be arbitrarily large, then you can universally approximate everything, like by extending the Soledad-Villar theorem. But how do you do it? So how do you write this parametrization? So one way people do it is by thinking, okay, the space of linear functions that are equivariant with respect to this group action is a linear space, right? It's just a linear space. So maybe what I can do is solve a big system of equations and get a parametrization by taking many elements in RD and many group elements. If I write many equations of this form and solve this system of linear equations, I can get a parametrization of the space of invariance, if invariant functions. That's what this paper by Finzi and collaborators did in ICML 2021. They basically say, if I'm going to use this neural network many times, and I want to just have the invariant functions or equivariant functions, I can solve this like system of equations for all the layers that I care about, and then that gives me a parametrization that I learn on the fly, and then I use it for training and tests and everything. Another way people do that is by using representation theory. So what they say is linear equivariant maps are in one-to-one correspondence between maps between representations of these tensor spaces. So they say, okay, if I have a representation by this group of this linear space, of this vector space, then I can decompose this representation in irreducibles, and then given two representations, I can map these two representations using this decomposition, because between two irreducible representations they are not isomorphic, or you can write the map as like a constant times the identity. So basically what they need to do in order to do this parametrization is take a representation of the spaces and then write them in terms of irreducibles. The maps are just given by just the composition of this group representation in irreducibles. And in order to do that, they need to compute this decomposition, which is not always very easy to do. But that's something that actually works in practice and is implemented for things like SO3, like the action of rotations in dimension 3. And these two people have two different implementations of that. And there's others, but these are the ones that So what I'm going to talk about is what we did for a paper in Units 2021 that gives a different way to parameterize the space of equivariant functions, but is restricted. It's simpler. It's much simpler, but it works in a smaller set of cases. Like it doesn't work in general for every group, but like this, if you can write the representations, then you can, like if you can decompose the product representations in irreducibles, then you can do this for any group. This is general, but this works specific for some groups like rotations and translations and Lorentz transformations and things that come from physics. And the idea, but it's very simple and the implementation is very easy. So I guess that's the advantage. So the idea is the following. So let f be a function that takes n vectors in Rd and outputs a real. This function is invariant, meaning that if I apply a rotation to every of the input vectors, then the function doesn't change for any rotation. And that's the functions that I want to parameterize. And then I'm going to parameterize the functions h that take n vectors in Rd and output a vector that is equivariant. So if I rotate the inputs, then the output rotates in the same way. So how do I do that? First, I'm going to say what groups do I consider. I consider the orthogonal group, rotations, translations, Euclidean, which is like rotations and translations, the Lorentz group, Poincaré group, and permutations. And the actions are what you expect. And so the main idea is just to use like classical invariant theory that gives us a characterization of what are the invariant functions. So a function that takes n vectors in Rd and outputs a scalar is OD invariant if and only if is a function of the pairwise inner products. That's like a very simple idea. The idea is that if I have the pairwise inner products, I can find the vectors up to orthogonal transformations by doing something like the Cholesky decomposition, and the solution is unique up to orthogonal transformations.
Is there any reason why you try to avoid to write this as a matrix space Rd to the n?
Yes, because then I'm gonna apply permutations to your inputs as well.
You permutate the vectors.
Yeah, because I think it's like this is like a particle system, right? So these n vectors in Rd are like n particles in dimension v, and so that now first what I do first is like I do rotations on your inputs, but then what I'm going to do is I'm going to apply permutations to the particles because all the particles are interchangeable. So that's why I didn't write this like d times n. That's just that notation.
I was just asking, so there are like some classical results in the algebra, which give you that unitarily or orthogonally invariant functions.
Yes.
Those are exactly the ones that can be written as a function that is sign permutation invariant as a function of the singular values. Yeah. I mean that's why I was asking why there's no matrix space, but I guess.
I mean, it's the same thing. This is like from file, like it.
Yeah,
like,
exactly.
Yeah. Mm-hmm. Yeah. Then the next question is, do we need to use all the pairwise inner products? And the answer is no, because you can use like the fact that you can reconstruct the vectors by observing O of n d plus 1 inner products by using like things like matrix completion. So far, this is like super classical, and I think everything is going to be super classical actually. So the next question is, how can you parameterize the equivariant functions? And then what you can show, and it's actually quite simple to show, is that if you have a function that takes n vectors in Rd and outputs a vector in Rd, this function is OD equivariant if and only if you can write it as a linear combination of your input vectors times a coefficient function, which is invariant. It's a scalar invariant function. This is also true for, I guess I should have said that in the previous slide. This is also true for the Lorentz group, but you need to replace the inner product by the Minkowski inner product that takes it's not a positive definite inner product, but it's just like the time coordinate, the product of time coordinate minus the inner product of the space coordinate. And so, and this you can also see that it has a similar way for like SOD, like for rotations, but you may have more terms in this expression because not every SOD equivariant function is on the span of the inputs, right? Like you can think, like for instance, in the sphere, you can take two vectors and the function of two vectors could be like the cross product. That thing is equivariant, but it's not in the span of the inputs. So you need to add other terms in this expression. But those are the only ones that will show up in SOD. And this is quite simple to see. It's very easy to see. You can prove that this is a polynomial, then these terms are polynomial functions as well. And this suggests a parametrization for the OD equivariant functions and SOD equivariant functions. But basically what it is you take your inputs, which are vectors, you can construct the scalar products, and then you learn these F1 through Fn functions. There are functions of the scalar products. And then you can do that with like some simple neural network, like something like an MLP that because here you're unconstrained, right? So here you wanted to have a function that was equivariant. But in this space, you can have any functions of the inner products, and that's the trick. Like you parameterize everything that is equivariant by just seeing that these things are equivariant. You can write it as any functions of the inner products, and then your output is just the linear combination. And that's a simple thing to like. That's a simple parametrization of the space of invariant functions that does not require you to like go to irreducible representations or do anything crazy. That's the idea. And so you can also extend this to like translations in a simple way. And if you want to look at functions that are permutation invariant, so say you have this particle simulation and you want to predict where the particle I is in the next step. So that's going to be a function of all the particles, but all the rest of the particles are permutation invariant for I. You don't care what order you give them to I. And then you can, a function that is in that way, you can write it as a function of, as a linear combination with the same coefficient functions for everyone, where this is a function that is a function of di and everything else. And this is like invariant. Okay. You can write it as message. So what do you do for general groups? And so what we did here is just like simple, like it was just like a simple application of classical invariant theory. And invariant theory tells you how you can parameterize the algebra of invariant polynomials. The question is this parametrization of the algebra of invariant polynomials efficient enough in order for you to write your invariant functions as a function of the generators of the space of invariant polynomials. So in particular, there is a specific decomposition of the space of invariant polynomials that is called the Cohen-Macaulay decomposition, which is basically there's like some primary invariance and some secondary invariance, and every invariant polynomial can be written as a function of the primary invariance times the secondary invariance, and that's the composition is unique. So if you have that your space of invariant polynomials has a basis that is small enough, then you can use it to generate the space of invariant functions and to parameterize the space of invariant functions. So in our case, in OD, if d is greater than n, we know that the invariant polynomials, the primary invariants are the scalar products and the secondary invariants are trivial. And that's basically what we're doing here. So in the case of the graph neural networks, the space of invariants is actually exponentially large. So you cannot use it as a parametrization in like neural networks. That's what's going on. So I have some examples of like the application of this parametrization for some specific problems. So in particular, in this example here, this is like a simple example where I have like a double pendulum with springs, and this system, you have like is given by the positions and the momentums of the two masses, and then the lengths of the spring and the constant of the spring, and then you can write the kinetic energy and the potential energy. And then this system is Hamiltonian, so this energy is conserved, which is in correspondence with some time translation symmetry. And then if I want to learn the dynamics of this system, I can think of it as an O3 equivariant functions if I think that the gravity is an input vector to my system. Because if I rotate the gravity with everything else, then everything rotates in the same way. So that's what we do. We parameterize this function as in terms of the scalar products of the input vectors, gravities, etc. And we use like a neural ODE or a Hamiltonian neural network to learn it. So basically the idea is you have the inputs, then you compute the scalar products, then you learn the Hamiltonian, say, which is a scalar function of all my vectors, and then I use a Hamiltonian integrator to predict the positions afterwards. And I obtain that it works well. And I compare with this software with this package EMLT, which I think is great. We extended this package to add our model, and we obtained that it has better performance than the other models that they compared to, like that they implemented. So one question that I'm interested is like, how can you compute, like how can you quantify how much do you gain by imposing the symmetries in your learning problem? And there's many ways you can think of this problem. I like the framework in this paper by Elizedi and Sadie in 21. What they say is the following. Say that I have a group acting in RD, and this group is compact. Then say that my data is sampled from some distribution in RD, which is invariant with respect to the group action. Then I have some training data, which are some xi's, and then yi's are some function of xi with noise. And I'm going to assume that my target, the thing that I want to learn, which is this f, is an invariant function. So if I'm doing a regression and I know that the target is invariant, right? Then what they say, okay, the risk of f is the expected value of the error with the data sample from the distribution that is coming from, and the generalization gap between a function f and the projection of f onto the space of invariant functions. So take a regression, linear regression, or whatever regression you have, polynomial regression. Take your output and project it onto the space of invariant functions. So if you do that, the risk of your projected function is always going to be smaller than the risk of your original function. And the amount of thing that you gain is the norm of your function that is in the orthogonal complement of the invariant space. So that's what you gain. That's how much you gain. So this tells you, like, if your target is invariant, you always gain something by imposing the invariance in some way. That's what it's telling you. Title of my talk was actually Units-equivariance, which is the example that I'm giving now. So in this example, the idea is the following. Okay, so I'm just gonna say it in the context of the double pendulum, just because it's a simple example. So what I'm trying to learn here is the Hamiltonian, which is an energy, and the energy has units, which is kilogram meter squares divided by second squared. And all my inputs to my function have units, like this, like I don't know, this is like newtons per meter, and this is like meters, and this is blah. Everything has units. So another symmetry that I didn't impose in my previous example was the symmetry of being units equivariant, meaning that if I multiply everything that has units of kilograms in my input, then my output, which was the energy, needs to be multiplied by the same thing, right? So that's a symmetry that you can enforce. And the way you enforce this is by using classical dimensional analysis. There's like this theorem that's called Buckingham-Pi theorem that tells you that every function that is units equivariant, you can write it as a function of dimensionless features multiplied by some factor that has the right units. So basically what you do is you take your inputs features, which are all these things, the meter, the masses and the velocities and everything that you have, your input features. Then you apply a transformation that makes these things dimensionless. For instance, M1 has units of kilograms, M2 has units of kilograms, so M1 divided by M2 is dimensionless. So you can construct a basis of dimensionless features, and then you can learn a function in the space of dimensionless objects, and then in the end, you just do the right scaling and you output the energy that you wanted. Does that make sense? So if you do that, then you see that actually for this example, what we obtained was that the error, experiment 1 is just like what we were doing before, like the prediction of the orbit from the initial conditions. The error that we obtained is actually larger than we obtained for the baseline in our previous experiment. And the reason why we obtained a higher error was because it was very hard to make it work, because you have to like, your dimensionless features are quotients of things, like M1 divided by M2. So if some of the things that you're dividing is close to 0, then it's very numerically unstable. So it's a complication. It's not like super it's not like perfect. But what we can show is that this generalizes much better to like out of distribution situations. For instance, the example that I told you before, take everything that had units of kilograms and multiply it by 5. That experiment had like very nice performance in the dimensionless, but in the other one, it couldn't really do anything with it. So this is like the plot that I have here. Like, okay, I don't know if you can see it very well, but like all the predictions are like along the orbit, but then in this case, like one of the predictions is good and the other prediction is like not good, because it's like, I think it went here and then it just did something crazy. Because it's out of distribution, so the learning doesn't work. So like I'm interested in like formalizing how you can show that doing this thing can give you like better out of distribution performance. Okay, and the other thing that I think is an interesting math problem is that this thing that we have here, like how much do we gain by imposing these symmetries, requires that the group is compact, but this group is not compact. So this theory doesn't really apply. And the question of like, what is the right projection onto the space of like you have a function that is not scaling invariant. What is the right projection onto the space of scaling invariant functions? There's something that doesn't really match. And the thing that doesn't really match is this one. So in the compact group case, you can define this Reynolds operator, which is projection of f onto the space of invariant functions by averaging over all the group elements f of g of x over g. And g is a compact group. So you can do this projection by averaging over the orbit of your group. And if the measure mu where you sample your data is invariant, then you can show that this averaging over the group is equal to the projection onto the orthogonal projection onto the invariant space from using the L2 of the measure that you sample from. So this is true in the compact group case, assuming that mu is invariant with respect to group action. But this is not true for non-compact groups. So the question is like, well, if you want to prove something like that, what is the right notion of projection? And I would argue that this is the right notion of projection for the group action, but this is the right notion of projection for the generalization error. Like how much, like how well do you gain when you train, or like how well does your method performs when you train from data sample from this distribution? So since these two things don't match, then this result doesn't really hold. Any comments or questions or anything? So what I talked about was like enforcing exact symmetries in machine learning models. I argued that you gain something by implementing the symmetries. At least in the compact group case, I give you a precise quantification of how much do you gain. In terms of generalization error, you can translate that in terms of sample complexity, like how many fewer samples you need. In the case of graph neural networks, what you care about is this like permutation equivariant with respect to permutations acting by conjugation. And this is connected with the expressive power of graph neural networks via the graph isomorphism problem. And in physics, we looked at equivariant functions with respect to groups like the orthogonal group and similar things. And we looked at the extensions to unit equivariance, and there's many open problems in this space. Something that I'm interested in is like exploring connections with the matrix completion stuff, and this formalizes out of distribution generalization thing that I told you earlier about, the stuff about like doing this characterization of the space of invariant polynomials for general groups. And can you use that for parametrizing other invariant functions, or is it computationally too expensive? So this is my talk, and those are my preferences.
Okay, thanks a lot for the wonderful talk. So any question in the audience or online also, if you have any question, you can unmute yourself. I don't know if you can see us right now because the camera is turned off, but hopefully you can hear us.
Okay.
Oh yeah, right. Now we're back. Okay.
Oh,
there is
Elliot.
Invariance or equivariance. I don't know if you thought about that issue, like if you just happy with the being just approximately this properties.
I'm interested about that.
If there's anything
I don't know if I have. Yes, for sure. I think there's a lot to gain, like in the sense that convolutional neural networks gain something over like feed-forward neural networks, and they kind of implement some approximate invariance. So I think that there's something to gain, but I don't know how you define it or how you quantify it. Also, learning the symmetry from the data. I think that's a very interesting question.
Yeah, that's what you
because
mentioned.
here I design all the symmetries that I care about. I say by design, these are the symmetries, but maybe there's a way you can learn the symmetries from the data and incorporate that into the design of your models.
So also for images, you mentioned at the very beginning of your talk that maybe this is, oh, there's a question here.
So for the non-compact groups, you are interested in, that I'm interested in, sorry. What do they look like? Is it possible they are dense in a compact group? Are they polynomially growing? So the groups that I looked at it are just the groups of scalings that you can think of them as the positive are non-negative, are positive times to the k. So are greater than 0 to the k. That's the group that I looked at. So so something that I don't know if they're polynomially growing. No, I think that they're fixed. But something that we looked at was that the compactification of the group. We looked at the definition of averaging. You can define this averaging by looking at the compactification of the group and look at it like in the complex plane. And there's like this Weil Unitarian trick that allows you to define this object. And you can define what is the projection of a rational polynomial onto the space of scaling invariant rational polynomials, and is very nice. But the issue is that this projection does not match this other projection. They only match if your data is supported in like the complex space, not in the real space. So that is a limitation of this, that I found that non-compact group may have. Okay, I don't know if I answered your question, but that's everything that I have to say. Yes, thanks.
I was wondering about images too, that you mentioned at the beginning of your talk. Okay, maybe images are not like, I mean, the way images are kind of projections of things that respect many symmetries, like objects and bodies. So like, I guess it's hard to, is there a way to kind of encode this property in the machine learning method? Like the thing is that it's kind of invariant to some kind of hidden symmetry that is not explicitly representable. So maybe it is related to what you were saying about learning symmetries from data. I don't know, but I feel like in images there would be path here too. It would be really powerful if there is two images. Actually.
Yeah, but I don't know how to do it, but it'd be, I think it's.
One question from the audience, yeah.
So I think if you apply the symmetry, this means the solution of the network is unique.
Can you ask that again? Sorry.
So it's like you apply some rule of the symmetry, right? So they are equivalent. And after we remove this equivalent set, so is the solution unique after we remove this equivalence?
Like if you're given the function f, and now okay. So let me see if I'm asking if I'm understanding your question correctly. So this, like, you're asking, is this f tilde unique? Is that what you're saying? I think so. Yeah, I think it should be unique.
Okay, so maybe let's just thank speaker again.